So this is what I would call weak dense disorder. But then there are disorders which are, I don't know, a foreign atom. Sorry. Epsilon is equal to infinity, epsilon equal to 0, epsilon equal to infinity. Okay? So these are very, very different physical problems. Right? Because in these problems, what happens is that a plane wave propagates thinking that life is good, and then it just scatters, and it remains a plane wave, and then it scatters again, and so on and so forth. Okay? Whereas here, the plane wave is constantly, right? So if you think of the, so here basically there's a well-defined KF in between the collisions, and it's all the same magnitude. Okay? Whereas here, the Fermi momentum is actually drifting, if you like. If you consider this to be a very sort of a gentle thing, you can think of it roughly. I'll put a quotation marks here because it's a bit, one has to be slightly careful in defining what spatially dependent K is. So you can see that, so this is what I would call a strong sparse disorder. I'm sure that's not the official notation, but I didn't have the time to look up in the literature. And you can see that here in this regime, this microscopic derivation is specifically for this regime, and so here we get the mean free path is 1 over disorder squared. But if somebody gave you a physical problem where the disorder had two values, 0 and infinity, right? So how does one assign a mean free path to that situation? And again, physically you might think that, you should think that these two situations is just, they're related, right? So any idea how you would, without solving anything, assign a mean free path to the second example? So it's the typical spacing between these. Turns out to be a typical spacing between these. So you can see that the mean free path is, is determined by simply the density of these strong scatterers. I mean, it's not so simple. It's I think the scattering cross section needs to be computed. I mean, it becomes more of a nuclear physics problem. I remember. So actually, this is actually very nice, because what happens is that this naturally lends you to the semi-classical description of the problem, and there are many papers on this. There's a big review by Albert Schmidt and Sudeep Chakravarti in the 80s, where they've tried to do essentially Chakravarti. They've 80s semi-classics for the localization problem. They've tried to do very carefully to derive the path and then go and see which cuts. Oh. Okay. All right. So that's all I'm going to say about the weak disorder regime. But I think the issues such as this one are sort of important to keep in mind, because at the end of the day, we do care about numbers. I'm not proving theorems. We care about numbers. All right. No questions. I will keep chugging along. So, strong disorder, to be precise, weak hopping. Right. In this case, in that case, there is a dynamical difference between the two, problems. Strong disorder and weak hopping is purely a matter of rescaling things and keeping in mind, I don't know what happened to the Hamiltonian here, that these things are trivially interchangeable.
So you're still defining what is not localization.
What?
So you're still listing of what is not localization.
No. I'm not defining things by what they're not. I define things I didn't define sharply localization. I just said that, look, there are things that behave in a very atomic way, in the sense that, if you have an atom, you try to excite it, unless you hit one of the resonances, you're not gonna, no energy is going to get absorbed. You have a, variance of the position, things don't run away. I think that's the level of definitions. I'm comfortable with this sort of a qualitative picture for now. I'll define things more precisely following Anderson 58. This is just an example that in the completely opposite regime, it's almost okay just to think of plane waves and how they get relaxed. And that's enough to get finite conductivity in it. Sorry, I'm not sure if I answered the question. Is it?
So what I'm saying is that this is not weak localization or strong localization.
There is no localization at all here.
Yeah, that's okay.
This is, if you like, this is the the kind of kinetic theory you would do in the late 19th century, except for quantum particles. What? Yeah. Right. Okay. Yeah.
Strong and sparse case, if we assume that the scatterings are not elastic, does it change the picture very much?
Yes.
It does?
Well, in the metal, you might think no. But I think that the whole sort of a notion of just doing quantum scattering theory assumes that there is, I don't, one has to agree on what formalism you're going to use if the potential is inelastic, right? Because if it's the kind of a classical time-dependent potential, that's one set of tools. If it's actually a real atom that's just sitting there with a discrete spectrum, every time you whack it, chances are nothing will happen. It's just going to ring a little bit. But if it's some kind of a bath, I don't know. I don't want to. I haven't even thought about that. But yeah. I think the general belief is that in the metal, you basically have plane waves to start with. Whatever simple perturbative approximate theory you're going to do, you just need one number. You need a lifetime, right? That lifetime can have interesting behaviors versus energy. It can have some other behaviors, but I think as long as you're just really trying to focus on getting one that's decay, some kind of a jazzed up Fermi golden rule is probably going to be okay. But that's, I think if you have a specific case in mind, that has to be sort of a track. Okay. Anyway, so what's the idea now? Forget about these extended considerations. Let's take just one locale of this. Right, so this is EM plus 1. So we're thinking of delta, which is EM plus 1 EM. And the idea is that let's call this 0. Right? And then this is a healthy energy splitting, so we can do second order perturbation, or first order perturbation theory, and write this as 0 plus T, and there may be other sides that are close to 0 within hopping distance. Right. Lowest order, that's all we have. So it turns out to be convenient to introduce. Did I leave something out? What? Ah, yes, thank you. Thank you. So interestingly enough, green functions actually played an important role. So for those of you who have forgotten, let me just quickly define what a green function is. what a retarded, I guess, green function. So I have a tendency to make a lot of mistakes, even with simple. Oftentimes it's safer just to copy, okay, definitions. And so the green function is just a matrix element of the resolvent, right? So it's 1 over E plus, or wait, minus, sorry, it's a disaster, plus I eta, okay? The green function satisfies the Schrödinger equation. The green function has, whatever we write about the perturbation theory plus dot, 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 a similar expansion exists for the green function. Let me not replicate it, except just to roughly indicate it. So green functions have an unpleasant feature, which is they include perturbative contributions which are disconnected in some sense. And that you can see, again, if you're familiar with this, that you can see in the same factor showing up in all of these corrections. So that sort of suggests resumming the green function perturbation theory using the self-energy. Again, something that we all at some point learned. Okay. And so the nice thing about this self-energy is that it also has a perturbative structure. Sorry, I should not. Okay, there's the shadow again. Sorry. Right. M infinity. I'm going to restore the previous notation, and I will explain it shortly. Okay. All right, so the idea is that we start in one place on the lattice, and we draw paths. These paths can have complicated sort of geometries, they can have loops, overhangs, but they don't have disconnected pieces. Okay? So the green function only contains connected paths. Paths connected to beginning and ending on the lattice that we're interested in. So this is M1, M2, M. Okay. There is a conceptual difference between these green functions and, sorry, what did I do wrong here? I did something wrong. So let me just keep going. Something bothers me. Sorry, the green function has in principle two indices. The self-energy that I want is the, so now I'm talking about the diagonal piece of the green function that begins and ends on the same side, hence the closed loops. Okay? Okay, so physically, so M is a local thing. Again, I don't know the origin of the term, whether it was invented by, in the 58 paper, local basis, so-called locator basis. So, in that case, where we had momentum space bases, our self-energy was just the lifetime, and that was sort of indicating how quickly the probability was leaking out of momentum states. Right. Here, the idea is that the basis is a local basis, so imaginary part there's a minus sign. No way I'm going to do that, right? So if this is finite, if finite indicates leakage of particles from site M. Okay? So I think at this point the goal of the calculation is to say something about possible behaviors of sigma. Okay? Self-energy. In other words, is it real? Is it imaginary? Can it be imaginary? And if you, where's the perturbation theory? Right. If you look at the perturbation theory, and you can try to compute this by limiting yourself to a finite order perturbation theory, you can convince yourself that it's never finite except for this infinitesimal. Right. So if eta is finite, then gamma is always finite. Always finite. But somehow that's not what we're interested in. Right? And so the question is that, suppose eta goes to 0, then finite gamma implies delocalization. So this is simple and important to just internalize. So I don't know, again, I can speak from personal experience just reading original papers. There's a stream of statements, and some statements are actually more important than others. Right? And one way to convince yourself that this is important in the context of the thing that's on the very first board is to look at this object, which is G. I'm not going to separately define it. It's kind of self-evident. Basically, the idea is that we're going to put a particle on site M and let the time flow. Right? So if the system, if you have an atom, when you put it in there, you're not going to put it into an eigenstate. You're going to put it into some configuration, some kind of a dipole sticking out this way, right? And it's just going to sit there and oscillate with a set of frequencies. So sigma going to 0 means that it's just a sum of frequencies that behaves, right, so some set of oscillators, and that behaves in a non-decaying fashion. If sigma is, imaginary part of sigma is finite, then you get decays. Actually, let me just take a specific form. So if imaginary part of sigma is, I don't know, it's constrained to some band. I don't know what letter to use, I guess delta E. Then G will be not too unfamiliar from Fermi golden rule. It will be decaying as a time with some numbers here, and I think because I put in sharp, there's actually some log corrections. So this is delocalization. All right, where are we on time? I started at 1:30, right? So I still have half an hour.
Can you just go back to answer to
What?
the answer to
The n?
eta, sorry.
Eta. Yeah, so eta, at this point, eta is just stuck in because of causality. That's how we define green functions, right? Yes? Then what's the question?
This would be.
So the point is that, if you have an atom, right? I mean, I think at least one way to, rather than saying things in general correct, just giving you examples. So let me try that. Right? If you have an atom, you can put eta there to define a green function of an atom. In the end, as you take it away, there's no decays. Right? There's basically